Hello everybody, and back by popular demand, I'm going to be doing a few more videos. I'm going to try and go through the 2017 midterm, and, if enough people comment about it, or, throw a like on the video if you're liking these things, I might try and fit in the 2015. So I've got the 2017 and the 2015 midterms up on OWL, as I've mentioned in class, and so I'm just going to go through the 2017, so last year's 1501 midterm, and we're just going to do one question per video. Same as we did with the last couple midterms, or just the last midterm. I've done a couple of these for other classes, but okay. So what have we got here? The 2017 midterm 2, so this is sort of gamma function power series things. Sometimes gamma function doesn't appear on midterm 2 if it appears on midterm 1, but it is something that we do test. We haven't had it on our midterm 1, so I'd expect to see it on our upcoming midterm 2, even if I don't know if there's any gamma function on here. Exactly. We can do a quick rundown. No. Convergence. No. True or false? Well, some true or false questions. Those are cool. No gamma function on this year's. But that's okay. Or not this year's, but this particular year that I'm going through. But doesn't change the fact that there is gamma function on the 2018 midterm that you guys will be writing. Alright, so just one question per video. Let's do problem number 1 to start things off. Of course, it's a natural thing to do. So, problem number 1, find the limit of the sequence. So we've got an A part, we've got a B part, both of them are worth 4 marks. So no particular reason to do one question over another. They're both equally likely. So for this one here, I've got an, and look at what I've got here. This looks a heck of a lot like sort of a polynomial over a polynomial. So it's a rational function. It's rational in n. Okay, now, what we might say is an is really just f at n, and define my f of x as 1 minus pi x plus 5x cubed. Turn it back into something that we're more likely to see in Calculus 1. So now I've got a nice, this is a rational function here. The pi is throwing me off a little bit, but it still is a rational function because it's got real coefficients, and it's polynomial over polynomial. Now, there's a nice result we learned in class, that if I can write the ANs as just a function f with the n plugged in, and the f of x is continuous for, well, really we need just eventually. Eventually it stays continuous. It's going to be fine in this case to say for x greater than or equal to 1. But really, you just need some cutoff. So if after 16 you knew this was continuous, that would be fine. The reason I'm hesitating about this is for a rational function, you should always be wary of the denominator and make sure that you're not including parts where that can be 0. But it can't be 0 for anything bigger than 1, so we're going to be fine. Alright, so if I can write my ANs like this, and not every sequence that you encounter can be written like this, but if I can write the ANs like this, and the limit of this function is, let's call it L, so suppose the limit does exist, then it turns out the limit of the ANs exists, and I would absolutely write this down. It shows that I understand the theory behind what I'm about to do. So, well, it turns out that the limit of these ANs is going to be exactly the limit of these f of x's, as x tends to infinity. And this is going to be the limit of 1 minus pi x plus 5x cubed, x plus 6x cubed. Now, we could say, hey, this is Calc 2, and the only way I get into this class is by passing Calc 1, and this is a sort of a common limit in Calc 1, so we could just jump to the answer from there, but I figure, why not show a little bit more work? This is worth 4 marks, okay? So I'm going to, multiply by what I like to call a sneaky 1, and in particular, what 1 am I going to use? Well, I'm going to take a look at the highest degree that I see. I see powers of x that are x cubed. So I'm going to multiply by 1 over x cubed, 1 over x cubed. So I might say 1 over x cubed, there should be an x there, minus pi over x squared plus 5, all over 1 over x squared plus 6. And then as x tends to infinity, this goes to 0, this goes to 0, this goes to 0, and we're left with 5/6. Very nice, neat. I'd put a little box around the answer just so it's very clear to whoever's marking that this is what I think the answer is. Okay. How about B here? Still worth 4 marks. Still trying to find the limit of the sequence. Now, because of the language of the question, they didn't say something like find the limit of the sequence if it exists. I'm shooting straight for there is a limit here. The question is, what is it? What is it? And I see a cosine here. Whenever I see sine and cosine, and it doesn't just have to be as a sequence. When I see them in series, when I'm adding up things involving cosines and sines, I start thinking of comparisons, just like I did when we were doing things with the comparison test with the integrals. So, I start thinking of comparing, and I know that cos n is bound between -1 and 1. This is useful when you're doing comparison theorem for improper integrals. It's useful when you're doing comparison theorem for series. And it's actually going to be useful here because we're going to do a little bit of a squeeze theorem. Okay, just a little bit of a squeeze theorem. Okay, same sort of rule applies. So I might say the BNs here are f at n with f at x being equal to cos x squared over 2 to the x, and this guy is continuous. It's continuous everywhere, but I don't really need it to be continuous in any particular place, so we'll just say greater than or equal to 1. Okay. So, what can we do? What can we do? Well, I can say quite confidently that cosine of x is between 1 and -1, and the cosine of x squared is going to be between 0 and 1. Okay, and then what can I say? If I divide by 2x on both sides, I'm dividing by a positive number, so the signs never change here. Now I've got 1 over 2 to the x, which is really just 1/2 to the x. Okay. Now the limit, as x tends to infinity, of 0 is 0. And since our base is less than 1, we know, probably from Calc 1000 you saw this, that the limit of 1/2 to the x, as x gets bigger, this is going to just get smaller and smaller to 0. So we have sort of that infinite squeeze that we've mentioned before in class. Okay. So we can say by squeeze theorem, since 0 is less than or equal to bn is less than or equal to 1/2 to the x, we see that the limit, as x tends to infinity of our, well, as n tends to infinity of our bx's, let's say this, f of x here, is going to be the limit as x tends to infinity of our f of x's, which must be 0. So the limit of the bn's is 0. Okay, how else could we sort of see this as we were approaching it? Well, trig functions like sine and cos are sort of bound by 1. They never get bigger than 1. We can think of them almost as being slightly worse than a constant term. And a constant over an exponent, the exponent's just going to get bigger, 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 but the top is staying relatively the same. It's bouncing between -1 and 1, but it never really takes off in any way. So it's essentially standing still as the top just gets bigger and bigger and bigger. So it's natural to realize, well, the BNs are just going to go off to 0. But with 4 marks in the line, we want to justify it a little bit more. Okay? So that does it for question number 1. Up next, of course, will be question number 2, and then 3, and so on, and I assume you know how to count at this point. So I will see you for question number 2 in the next video.